Okay, so today in class, you had a chance to tackle one of the most difficult problems, well, we've seen so far in magnetism anyway. The reason this problem is so difficult is not because the integration is difficult, and, well, in fact, the integration is trivial, it's super simple. The reason this problem is difficult is because you have to think in 3 dimensions, and there are so many angles involved, 3 to be exact. So, the problem is to calculate the magnetic field from a loop of wire. And the way this problem is set up, you have a loop of wire that is oriented in the plane of the XY axis. So this is a plane, the Y axis is running vertically, and the X axis is running into and out of the page. Which, if you look at that, that means the Z axis is to the right side of the page. Well, if you do the right-hand rule on that, you'll realize that the field at point Z must be pointing, the field at point P must be pointing in the direction of the Z-axis. So, that's where we're starting. So we want to determine the field strength at point P from the loop of wire. So, to do this, well, we've got to realize a few things. First of all, the field at point P from any little piece of the loop, somewhere on the edge, I'm going to pick the top spot on the loop right here. The field from the charges flowing at that point, the charges are flowing at that point in the negative x direction. But if you think about it, that charge right there is going to create a field at point P that doesn't quite point along the z-axis. Rather, it points at some weird angle up. It's actually a 90-degree angle formed by the r vector, which is this vector. It's got to be perpendicular to this r vector and to the v vector. So it's got to point that way. So what I did in this problem is I set it up, I called this angle in between the r vector and the z-axis, I called that angle phi. Alright, so that's angle phi. And what that means is the angle that this field points up at, this angle is also phi. The little triangle formed right here is a similar triangle to this triangle right here. The reason that's important is, if you think about it, if you were to add up all the contributions to every point along the circle, well, each point is not going to be, the field from each point along the circle is not going to be facing in the z direction. It's going to be facing some crazy angle to the z direction. But if you take the top point, it's pointing up this way. If you take the point down here on the bottom, it's pointing down that way. Well, that means for every charged particle up here moving in the negative x direction, perfectly cancels out with the field from a charged particle at the bottom moving in the positive x direction. The y component of that field is balanced by the negative y of this field, and the result is just a component in the z direction. And every point along the circle has a counterpoint on the other side of the circle where the non-z components cancel out. So in the end, what we're interested in is just the z component of all of these fields adding up, because everything that's not along the z direction, along the z-axis, cancels. Alright, so in the end, what we are interested in is the field only in the z direction. And once you realize that, then you can start doing the problem. Alright, so what I have set up here is the basic equation. The field in the z direction from a particle is mu naught over 4 pi Biot-Savart Law, IDL cross r over r cubed times sine phi, where phi is this angle. all right, or this angle. Now, in order to get that angle, what you have to do is it's a sine, right? We're interested in this component. That's the opposite. This is the hypotenuse. So I need sine. So phi is opposite over hypotenuse, which means the opposite is the hypotenuse times sine theta, right? Or, well, sine theta, if that angle is the same as this, and you can prove yourself that with geometry, if this phi is equal to this phi, that means phi sine of this angle is equal to the radius of the circle, capital R, over little r, which is the distance from the edge of the circle to point P. So sine phi in the end would be capital R over little r, or capital R over square root of z squared plus capital R squared. All right, so we need to put that term in. All right, so back down here at our basic equation, that's our sine phi we just talked about, and this is the Biot-Savart law that we know. Now, we know that the Biot-Savart law, you always end up converting IDL cross R over R cubed into IDL sine theta over R squared. All right, and the sine theta comes from the cross product. Well, we haven't talked about theta yet. What theta actually is, if we go back to the picture, theta is actually the angle in between the direction that the charges are moving, which in this case is along the negative x-axis, and the r vector, which is this way. And if you look at it for a second, you can convince yourself that in fact that angle is 90 degrees. And if that angle is 90 degrees, that means that anywhere along the circle, the angle in between the direction of charge motion, or the direction of the current, and the r vector is also 90 degrees. Well, if it's always 90 degrees, that means it's always constant. And the sine of 90 degrees is 1, which means we don't even have to worry about the sine of 90 degrees. We just write in 1 for that. So in the end, this equation becomes IDS times 1 over r squared times the sine of phi. Now, we're going to do a little mathematical manipulation here. First, we're going to realize that in order to integrate, I want to integrate around a circle. Well, what does it mean to go around a circle? What that means is integrate from here all the way around to there. Now, there's a couple ways to do that, and the way I've chosen to do that is to say, well, the angle is going to start here at 0 degrees and then go around all the way to 2 pi around the circle. We need a name for that angle. I'm calling it alpha. So alpha goes from 0 to 2 pi all the way around. So alpha goes from 0 to 2 pi. Alpha will be our variable of integration. So let's look down at it again. Now, well, alpha, I need to convert length along the edge, that's an arc length, into an alpha. So the way we convert arc length into alpha is to say that the arc length, or dl, is equal to the radius d, this should be an alpha, not a phi, r d phi. So let me write that a little bit more clearly. All right. D R D alpha. So ds is equal to rd alpha. So dl is equal to rd alpha. So anytime we see dl, we can replace it with rd alpha. So here we go. We've got, instead of writing ds, or dl, where you write ds, instead of writing ds, we write rd alpha. So we've got mu naught over 4 pi I times rd alpha, still sine phi, over r squared, lowercase r squared. Then we say, well, we already know what little r is, which is the Pythagorean theorem, square root of z squared plus capital R squared. So put that in. Then we're going to replace that sign of phi with capital R over square root of z squared plus r squared. Then do a little bit more simplifying. Combine the capital R's to get r squared. Combine the denominators to get z squared plus r squared to the 3/2. And then we look at all of these things and realize every single one is a constant. I is constant. The radius of the circle is constant. Z, which is the distance of the point from the center of the circle, is constant. The radius of the circle is constant. The only variable is alpha, but alpha isn't even in this. So we're going to integrate from 0 to 2 pi of 1 d alpha. And so we end up with just 2 pi for the integral. So that was easy. So the final result is mu naught I r squared. See, the pi's cancel. And that becomes 2 on the bottom times quantity z squared plus r squared to the 3/2 in the z direction, which is to the right in this picture. And that's our final answer. All right, so we now have a function of b as a function of a z or r or I or whatever else you want to call it. Example, what if we had 100 loops? All you'd have to do is multiply this by 100 and you get your answer. All right, last thing I wanted to point out here is, what if you were looking at the center of the loop? So let's look back at this. So what if I, instead of saying I want to know the field out here, I said I want to know the field right in the middle? What would z be? Well, z would be 0. And what that means is our final answer would be completely simplified. That z would go away because it's 0. And I get mu naught I r squared over 2, this would come out to r cubed. So for the center of the loop, it would be mu naught I, r squared over r cubed, so r goes on bod, over 2 capital R. Much, much simpler. And you're going to see a lot of problems that use this basic idea, mu naught I over 2r. All right, and that's it.